Welcome, this is Mrs. Nearing, and we're going to talk through part 3 of this acid-base review. We're looking at some topics related to buffers and acid-base reactions. This is just a sampling of some problems you might see. So one thing is we want to be familiar with these acid-base titration curves. So let's take a look at these here. So we've got 3 curves here where we are looking at the pH as we are adding another substance. In this case, we're adding sodium hydroxide. And notice how we are starting with a low pH and ending up with a high pH. So it looks like the substance being titrated is an acid. And the equivalence point is the point at which all of our initial substance, in this case our acid, has been used up. And the way that we identify the pH curve, the equivalence point on one of these curves here, is we look at this vertical region and we look at about the midway point of that vertical region will tell us the pH at equivalence. So I'm going to approximate, it's around 8, 8-ish. And notice how it is a basic at equivalence. So the pH is greater than 7. That tells me that the acid that we are titrating must be a weak acid. Because if this is a weak acid that we are starting with, let's write out this titration reaction that's occurring. So you got your weak acid, so it does not totally dissociate. You're adding hydroxide to it, and the hydroxide is going to take a hydrogen from my acid. It's going to leave the conjugate base. And if you have a weak acid, its conjugate will be a weak base. So there's a rule kind of weak pairs with weak. So the conjugate of a weak acid is going to be a weak base. So therefore it is going to be basic at the equivalence point. So that is how we know that it is a weak acid, is because at equivalence, you are left with a weak base. The pH is greater than 7. Let's go over and compare it to this next one here. So this one, it looks like I am starting with a high pH, and we're adding acid to it, and the pH is dropping down. So it looks like I'm starting with a base. And the question is it a weak or a strong base? Well, let's look at its equivalence point. The pH of the equivalence point here, I'm going to estimate it's around like 5.5. So that means that I'm starting with a base, and when I titrate a base, I'm adding a strong acid to it. So I'm basically adding hydrogen ions to it. And when I add a hydrogen to a base, I am left with the conjugate acid. And if what we start with is a weak base, then its conjugate acid will be a weak acid. So we will notice that the equivalence point is going to be acidic. So the pH is less than 7 because BH plus is a weak acid. Therefore, its conjugate was a weak base. So I know that I must have started with a weak base. So far we've seen 2 examples of weak things. Let's scroll over to this third one. So again, we've got a graph where we're starting with a low pH and it is going high. So that, and I'm adding, doesn't tell me what I'm adding, but I can tell I must be starting with an acid because the pH here is starting below 7. And then to figure out if that acid is weak or strong, I'm going to look at what is the pH at the equivalence point. And at the equivalence point, the pH is 7. So it is neutral at the equivalence point. And that tells me that this acid must be a strong acid. And let's look at why. A strong acid we can represent just using H+, because strong acids totally dissociate into H+ and whatever other anion there. And as I add my base to it, I'm going to make water. And so notice how when you titrate strong acid with a base, you end up making a product that is neutral. So there you go. Okay, so you always end up, another way of thinking of it is like you always end up with the conjugate of what you started with. So if you start with strong, its conjugate will be neutral. If you start with a weak acid, you will end up with a weak base. So this one's going to be basic at equivalence. If you start with a weak base, you're going to end up with a weak acid at equivalence. So the pH is low. But if you start out with a strong acid, you're going to end up with something neutral at the equivalence point. So the pH at the equivalence point tells us whether what we are titrating is a strong or weak acid or base. Another thing related to pH curves is, let's say that we want to run this titration here and we want to do something quantitative, like we're trying to figure out the concentration of an unknown, but we don't have a pH meter, so you want to use an indicator instead. You want to choose an indicator that would change color at the equivalence point. So let's say I'm titrating this acid. I want to know at what point does my acid all get used up. I would want to choose an indicator that's going to change color to around pH 8, somewhere there. So I've got a variety of indicators here to take a look at. And the indicators are actually themselves weak acids. So you see there's a pK value given for the indicators. And that tells you the color at which, the pH at which it's changing color. So I want to choose an indicator that's changing color at around pH 8. I've got one a little bit, above or a little bit below it. I'm probably going to want to choose we often choose phenolphthalein. Notice how it changes color around 9. This is often a good choice. Let's see, where's phenolphthalein? Here's where it is there. So you see it changes color right around pH 9. This one's a nice one to use because it's really easy to see that color change. Thymol blue would work out as well. So either of these would maybe be reasonable ones to choose when you're titrating a weak acid. So I'm going to write down phenolphthalein. Phenolphthalein, I know it's a hard one to spell because it will, change color at around pH 9. I don't have any options that are changing exactly at 8, and that's okay. I just want something close. How about this one? Weak base is going to, its equivalence point was around at 5.5. So I look over at my graph, or if I look over here, it looks like maybe one of these ones would be good to use. So ethyl red or resorcin blue. Let's see what these look like. Here we go. I could use this one, or I could use this one. I kind of like the look of ethyl red because it looks like a nice dramatic color change. I personally haven't used that one before in real life, but it looks cool. And then let's look over here with your strong acid. So I would want something that changes color at the equivalence point. Notice with your strong acids, though, this like steep vertical region. So really lots of indicators would work. So something that changes color at pH 5 or pH 7 or pH 9, they're all going to give you the same volume reading. So there's actually a lot of indicators that would work well. Really kind of anything in this range here would work well. So a lot of times you might think that, maybe BTB, bromothymol blue, would be the best one because it changes color at right around, pH 7. But a lot of times people still use phenolphthalein because even though it changes color at a higher pH, that pH change happens so rapidly when you're titrating a strong acid that it actually still works out well as an indicator. So there's a couple things about titration curves. And then here's some more titration curves we can take a look at. So something else that we can find from our titration curve is we can use it to approximate the pKa for an acid. So if you remember what we were talking about earlier, if you're titrating an acid, initially you have pure acid. At the equivalence point, all of your acid has turned into the conjugate base. And that means when you're at the halfway to the equivalence point, that means half of your acid has turned into the conjugate base. And so you have equal amounts of HA and A minus. And because of this mathematical relationship with your Ka expression, and we find that when your HA and your A minus are equal to each other, pH is equal to your pKa. So at this point in your titration curve, this half equivalence point, your pH equals your pKa. So on this graph, it looks like my equivalence point is around 40 milliliters. So half equivalence happens at 20 milliliters of base added. And I'm going to estimate that it looks like it's around 7, maybe like 7.5. We have to estimate, so somewhere 7 to 8-ish looks to be the pKa of this acid. Now let's look over to the second acid on the right. It looks like its equivalence point is happening at 30 milliliters. So its half equivalence is maybe right around here at 15. And so it looks like its pKa, I'm going to say it's a little bit less than 6, so I'm going to approximate that's maybe 5.5. So half equivalence point will tell you the pKa of the acid you are titrating. And then we can use that to make some inference about which is a stronger acid. Because if you look at our definition of what is the pKa, where's my equation sheet? No. Anyways, it tells you on your equation sheet that I'll just rewrite it here. pKa is the negative log of the Ka. So you can do the inverse. Ka is 10 to the minus pKa. So what that means is for this acid, the Ka for this acid right here is about 10 to the negative 7. I'm just going to round that. And then this acid over here has a Ka of like 10 to the negative 5th. So the stronger acid means it has a larger Ka value. So this is a larger Ka value. So stronger acid equals larger Ka value. If you said something about this acid having a lower pH initially, and that makes it a stronger acid, we can't necessarily infer that from this data because we don't know what the concentration is. They don't give us the concentration off the bat. You kind of have to do a little bit more work to make that justification fly. But you look at the Ka, the pKa tells you the Ka, so you can just figure it out based on that. That's kind of the easiest way to answer this question. And then let's look about the question of which acid is more concentrated, because notice they don't tell us the molarity of the acid. It just says we have two different acids of the same volume, and we're titrating with the same base, but we don't necessarily know if these acids have the same molarity. So what we should notice is the acid on the left took 40 mils of base to neutralize, and the one on the right only took 30 mils of base to neutralize. So since we're trying to figure out which is more concentrated, so the acid on the left, it took more base to neutralize the acid, so this one must be more concentrated. If we want to do the math, we could go through and actually figure out the concentration. So we could use this balanced chemical equation, and we could say, okay, it took 40 mils of 0.1 molar NaOH to neutralize our 50 mil sample of our acid. So we could figure out how many moles of hydroxide that is, and say, oh, they react in a 1-to-1 ratio, so we could figure out the molarity of our acid. But we don't actually have to do the math here, because it's just asking which is more concentrated. And so since these are both, a thing I should have mentioned here, these are both monoprotic acids. Well, I guess you can tell from the graph. They're both monoprotic acids, which means that the formula is just HA, which means they both have the same general equation happening. The base reacts with it in a 1-to-1 ratio. So what it tells us is that if it takes more base to neutralize it, that means there must have been more acid present in the solution. So this sample must be more concentrated than this sample. So the sample on the right is a stronger acid, meaning it has a larger Ka value, but it is also more dilute. So there's a difference between acid strength, which is related to the K value and how much it dissociates, versus concentration. So we don't want to get those two terms confused, because sometimes people use those interchangeably and they're not the same thing. So acid strength refers to the K value, and the concentration is the molarity. And you could be a strong acid and be really dilute, or you could be a weak acid and be very concentrated. All right, so let's look at another last titration one. So we've got a 0.23 sample of an unknown monoprotic acid being titrated with sodium hydroxide, and we find that it takes 23.5 mils of NaOH to reach the equivalence point of the titration. So we're getting some data that's kind of similar to what we've got up here. And this is a chemical reaction. So if I'm not given the equation for this chemical reaction, then I'm always going to write it out. So I got to make sure I know what's happening here. So it's my weak acid is reacting, there we go, and since it's monoprotic, it just takes one hydroxide to react my one hydrogen, so they're going to react in a 1-to-1 mole ratio. All right, and then when I do a little stoichiometry, my first step is always going to be to find moles. Okay, so I ask myself, what do I have information that I can use to find moles? So I've got a grams here, but I don't know the identity of this acid, so I can't find moles of the acid because I don't know its molar mass. That, in fact, is the thing I'm trying to find. So what else do I know? Well, I know the molarity and the volume of NaOH. And we know that since molarity is moles per liter, if I take the molarity times the liters, it will give me moles. So 0.115 molar times 0.0235 liters gives me moles. And the reason why that works, again, is molarity is moles per liter. So notice how liters cancel. All right, so again, bear with me. I'm going to do this in my calculator along with you. Times 0.0235. Okay, so that's 0.0027 moles of hydroxide. I'll write out the whole thing, sodium hydroxide. And I'm trying to find acid. Okay, so I know based on my balanced chemical equation, they react in a 1-to-1 ratio. So for every 1 sodium hydroxide is going to react 1 of my acid. So that means I also have 0.0027 moles of acid. And then I want to find the molar mass. So the molar mass is going to be the grams per mole. So my grams is 0.230 grams, and my moles is 0.0027 moles. And so I plug that in, 0.23 divided by 0.0027. I'm going to get 85. Let's see, how many sig figs should I have? I should have 3 sig figs, it looks like. 85.2 grams per mole as my molar mass. All right. So those are some titration based, facts here. All right. So thanks for watching.